G'day viewers. In this segment we'll talk about how to release connections. Well, we've talked about how to set up connections with TCP, so now it's time to talk about how to tear them down. In connection release, the main task is to close down both sides of the connection in an orderly way so that all of the pending data is delivered before both sides hang up, as well as cleaning up any state that's left over in the sender and receiver. So the key problem here is to provide this reliability to deliver the pending data in a nice clean way while doing the release. In TCP, we use what's called a symmetric close to handle this problem, where either direction of data transfer closes itself independently. So it's possible to have connections which are half open temporarily on the way to being closed. So here's how connection release works with TCP. To ensure that the data is delivered properly, we don't want one side or the other to simply just hang up anytime it wants to. When one party decides to end the connection, that's called the active party, they proceed with this sequence. They send what's called a fin to the other side. It stands for finalize. X, the sequence number here, will be whatever sequence number we happen to be at in the connection. So it's not a random number like it was for opening the connection. And the other side will then act this, and again it will act X plus 1 because the fin is considered to occupy 1 byte of sequence number space. And we're going to act the next expected byte. So at this stage, the connection has been closed in the direction from the active party to the passive party, but it's only half closed. We also have to perform the second step and do the same procedure in the reverse direction. So the second party now, when it decides that it's had enough with this connection, because after all, when one side hangs up, there's really not much more you usually want to do, the second side will send its own fin. That will have a different sequence number Y, and the active party will wait until it can be act, and at this stage the connection is closed. You could imagine that this fin and ACK in the middle could be combined if you like. Often they're separate packets just because of the logic, but they could also be combined into one packet as they were with the SYN and the ACK. Here's a cleaned up version of that diagram just to show you. I note here that the fins can be retransmitted if either of them were lost. Just like all data segments, they can be lost. So if you want to do something with them, you might need to provide a little bit of reliability. And just like the connection establishment, there's also a part of the connection state machine that's used for releasing the connection. As before, both the parties, the client and the server or whoever is interacting, run their own instance of this state machine. And to hang up, we want them to both move separately from the established state to the closed state. This is the release that we want. We just have to get there somewhere. Let me also remind you that in the state machine, rectangles, such as the ones I've outlined like established, are the states in which the connection finds itself, and the arrows between them are the transitions. The first portion on an arrow is the trigger action, such as receiving a fin segment. And the second portion on those transition arrows after the slash is the response or the action that the party takes, such as sending an ACK. Okay, so let's use this state machine just as we did for connection establishment, and now look at how the active party can close the connection in the direction from itself to the other side. We're going to start in the established state, because that's where we were when the connection was running. The active party decides to do a close, calls the close socket call. That's here, and that's going to take us on this path. As part of this transition, we send a fin packet to the other side. Now we're in the fin wait 1 state. We wait in this state for a little while, and what are we waiting for? We're waiting to receive an ACK from the other side. When we receive an ACK from the other side, we need to take no actions and we move to the fin wait 2 state. Here, what are we waiting for? Well, actually, by this state, we've closed the connection in the direction from ourselves to the other side, and we're just waiting around for the other side of the connection to close the other direction so we can clean up all of the state and go home. That will happen when the other side sends a fin here. When we receive that, we'll take this transition path, we'll send back an ACK, and we'll go into a time wait state. And then later, after some amount of time has passed and a timeout occurs, we'll go to the close state and we're done. I'll get to that timeout in just a moment. You can see here, by the way, that there's a different path through here. If I just look at this arrow here, you can see this is what happens if you combine the fin and the ACK together. We still get through the state machine in the right way. The right thing happens. Let's look at the passive party. It started in the established state. And then at some stage it received a fin from the other side. That's this input here, which caused a transition to this state, a passive closed state, and we replied by sending an ACK. The other side doesn't want to talk to us anymore. We've acknowledged that. At this point, the transport layer is in the closed wait state, and it's just waiting around. And what it's waiting for is the application to realize that no more data is coming in on this direction of the connection. If the app calls receive, it will find there's no data there, that the connection's ended. The app then at some stage will issue a close socket call. That will move us down to this state. We'll send our own fin, we'll go into the last ACK state. We will wait. What we're waiting for is to receive an ACK from the other side, the ACK for our fin. That will take us through here to the closed state. And we don't have to do anything, we simply move to this state and the connection has been closed. Yes, so both sides, the client and the server, have now both gotten from established to closed. By the way, either of them could have chosen to close the connection first. Which case occurs just depends on the application protocol itself. And here is another version of the time sequence diagram we looked at before with all of the different states on it. So you can see how we moved from established here to here. The close must have been called. That caused us to send the fin, move through states, and then progress through the states as new packets were added. On the other side, after we had received the fin and sent back the ACK, we went into the closed wait stage. At this stage, our app should work out that something is up and that there's no more useful information on the connection and call close. And when it does, we'll send our fin, get our ACK back, and we're done. Now you might notice there is a timeout state here. So a period of time elapses between the last action there and entering the closed state on the active side. What is all of this about? Well, this timeout is potentially a long wait. We actually wait up to twice the maximum segment lifetime. The maximum segment lifetime is the largest amount of time it can take a segment to be delivered through the network. So we're really waiting just in case there are any last packets going on. What could have happened is that an ACK might have been lost, the ACK we sent. In that case, sometime later we will get a fin from the other side. So we're waiting around just in case that happens. If that did happen, then we would like to catch that fin and respond to it so that we'll have a nice orderly close and tear the connection down properly. If we didn't, we might interfere somewhat with a subsequent connection. And that's why TCP uses a time wait connection, just as a bit of a trade-off to go the extra mile to try and make sure that the connection is being closed properly. And now we've torn down the connections.